right, so here should be a fairly quick look at a simulation of what a circuit would look like in motion. Now this is from PHET, PHET, Colorado. You can look up their website. You can play around with circuits on there. I've constructed a small series circuit here where you can see the electricity has one path to flow through, and that's it. I have a battery. I have two light bulbs. I have my ammeter to measure current, and I have my voltmeter to measure voltage. And I have here a switch. When I open the switch, look at that. There's no connection between this side and this side. The current cannot flow through. Everything stops. The instant I do this, the electricity flows again. So me toggling this on and off is the same thing as you flipping on a light switch in your house, or pressing power on your blender or whatever. That is the same thing as doing this. Now we see the electricity flowing through here. We can click and see, okay, this battery has 9 volts, and if you play around with this website, you can modify the voltage to whatever you want, but its default is 9, so I'll just leave it there. Why not? We have 9 volts flowing through this battery, or sorry, 9 volts is the voltage of the battery. We have 2 light bulbs. Light bulbs have resistance, so they're like a resistor. They each by default had 10 ohms of resistance. Notice my ammeter is detecting the amount of current flowing through it at 0.45 amps. Now on the right side of my screen, I'm going to show you the math for how we can calculate that, and we should be comfortable by now, at least somewhat, based on what we've gone through. So we have the total voltage is 9 volts. We have the total resistance equals the resistance of one plus the resistance of the other. I guess I don't know why I wrote 10 ohms there. So 10 plus 10 equals 20 ohms. So we have 20 ohms of resistance. Our formula was voltage equals resistance times current. We're trying to calculate current, divide both sides by R, and so we get current equals voltage over resistance. And so yeah, this should have been an R instead of writing the ohm symbol there. And so voltage of 9 volts divided by 20 ohms. This equals, if you punch it in your calculator, 0.45 amps. And so, lo and behold, we detect 0.45 amps. There is one path in this circuit for the electricity to flow. And so it all has to flow the same speed, and I'm calling speed current, the same speed throughout the whole thing. I have another ammeter here just to show, and I'm going to put it connected to, and I know it looks kind of wonky, but we're still connected in series, one straight line, and notice the current here is still 0.45 amps because it has to travel all the way through the same circuit at the same time. You open the switch, everything stops, or if you wanted to simulate, burning out a light bulb, so when the light bulb burns out, this filament literally breaks, kind of like a fuse, it breaks in half and electricity can't flow through there. That would look kind of like this. The light bulb broke. The electricity can get to the bulb like this, but it can't get through the bulb, so it can't leave. And notice there's no more electricity flowing anywhere. This bulb has turned off as well because the circuit was broken here. As soon as you cut this off, throw it in the garbage, replace it with, I don't know where, is that just it? Replace it with another bulb that has a proper filament, and hooray, electricity restored. So this is how a simple series circuit works. Now, the last thing we want to do, I'm just going to cut this out to make it a little bit smaller, back like it was before, to be more compact and whatnot. This is the current. The ammeter. The ammeter is measuring the current in series, meaning the electricity is flowing through it, like this. Now we have a voltmeter sitting here. When you measure voltage, sorry, I'm just trying to get the click off of that. There we go. When we're trying to measure voltage, we have to measure voltage in parallel, meaning we're not letting the electricity flow into here and connect it so it can flow out. So like, for example, what that would look like is if I were to disconnect this wire and connect this here and connect this here, to have electricity flow through it, that's not how you detect the voltage. So we have our, there we go, we've got our current flowing again. We connect this in parallel to two sides, like opposite sides of the circuit basically. So I can either put one here and one on the other side of the battery. Remember I said it was a 9-volt battery. Oh my gosh, it's detecting 9 volts. That's incredible. Or I can set it kind of on either side of my light bulbs. 9 volts. You're trying to detect the potential difference between the side where the electricity is coming out of and the side where the electricity is returning to. Now notice what happens. So it says 9 volts. Notice what happens when I put this here. It says 4.5 volts. You won't have to do any calculations or understand necessarily why that happens, but the positioning matters so that we're trying to detect, again, the portion coming out of the power source and back to the power source. Positioning this here is not positioned on the way back to the power source. It's positioned in the way getting to the second light bulb. When we go here, we'll find the full potential difference of 9 volts here. So this hopefully is a fairly quick explanation on how current works, how resistance and voltage work, how to measure voltage and current in a series circuit.